Imagine you're a tiny boat floating on a river. Near the middle, the water is moving super fast. But as you get closer to the riverbank, the water slows down a lot. It's almost like the bank is grabbing onto the water and holding it back. This slow-moving area right next to the bank is a lot like what happens in fluid dynamics when air or water flows over a surface, like a car or an airplane wing. We call this slowdown zone the boundary layer. It's a super thin but incredibly important layer of fluid that sticks to the surface, and it's where all the action happens. So, where does Y+ come into this picture? Think of Y+ as a special ruler that helps us measure distances inside this tiny boundary layer. It's not your everyday ruler that measures in inches or centimeters. Instead, Y+ is a dimensionless distance. That sounds a bit complicated, but it just means it's a smart way to compare the distance of a point from the wall to the tricky, turbulent forces happening in the fluid. It tells us how far we are from the surface in a way that's meaningful for the physics of the flow, no matter if we're looking at a tiny pipe or a giant airplane. This special ruler helps us understand which part of the boundary layer we are in. Close to the wall, where the fluid is slow and sticky, the Y+ values are small. As you move further away from the wall and into the faster-moving fluid, the Y+ values get bigger. It's like a secret code that tells computational fluid dynamics, or CFD, software, such as ANSYS, exactly where it is inside this critical region. Getting this right is the first step to creating a simulation that actually matches what happens in the real world, which is what engineering is all about. Essentially, Y+ is the secret ingredient for our simulation recipe. It's a normalized distance that tells us how fine our computational mesh, or grid, is near a surface. Think of the mesh as a fishing net that we cast over our object to capture the fluid's behavior. If the holes in the net are too big right next to the surface, we'll miss all the important details happening in that slow, sticky boundary layer. Y+ helps us make sure our net has tiny, fine holes exactly where we need them the most, right up against the wall. Now that we know Y+ is our special ruler for the boundary layer, let's talk about the magic number. 1. In the world of CFD simulations, especially when using powerful software like ANSYS, you'll hear engineers and scientists talk a lot about keeping Y+ around 1. Why is this one little number so important? It's because it allows us to directly resolve what's happening in the most critical part of the boundary layer, the viscous sublayer. This is a super thin region right next to the wall where the fluid flow is smooth, predictable, and dominated by stickiness or viscosity. Think of it like trying to watch a movie. If you're watching a high-definition movie, you can see every single detail, every eyelash, every tiny expression. That's like having a Y+ value of 1. Your computer simulation is capturing all the fine details of the flow right at the surface. However, if you try to watch the same movie in very low resolution, all those details become a blurry mess. You can get the general idea of what's happening, but you miss the important nuances. That's what happens when your Y+ value is too high. Your simulation misses the crucial physics at the wall. In ANSYS, you have different tools, called turbulence models, to predict how the fluid will behave. Some of these models, particularly those designed for high accuracy, are built with the expectation that you will give them a super detailed view of the wall region. They need the first data point of your simulation mesh to be placed squarely inside that viscous sublayer. A Y+ value of approximately 1 ensures that this first mesh cell is exactly where it needs to be, allowing the physics solver to directly calculate what's happening without having to guess or use approximations for that first layer. This is why setting up your mesh correctly is such a vital step in any simulation. It's not just about creating a grid, it's about being a detective and placing your observation points, the mesh cells, in the most strategic locations. By aiming for Y+ approximately equal to 1, you are telling ANSYS that you want the highest quality data right where it counts the most. This commitment to detail at the wall is what separates a good, predictive simulation from one that might look pretty but doesn't reflect reality, ensuring your results are trustworthy and accurate. Let's zoom in even further into that mysterious boundary layer. This region isn't just one uniform block of slow fluid, it's actually made up of different layers, each with its own personality. Right up against the surface is the star of our show, the viscous sublayer. Here, the fluid moves in smooth, beautiful lines, almost like layers of honey sliding over each other. The fluid's viscosity, or its internal friction and stickiness, is the boss in this zone. The flow is laminar, meaning it's orderly and predictable. This is the place where the transfer of forces and heat from the fluid to the object begins. To accurately predict things like friction and heat transfer, we absolutely must understand what's happening in this viscous sublayer. And the only way to do that with high fidelity in a simulation is to place our measurement points directly inside it. This is precisely what aiming for a Y+ value of about 1 accomplishes. It ensures that the very first computational cell of our mesh is nestled snugly within this calm, laminar region. By doing this, our CFD software doesn't have to rely on assumptions or generalized wall functions to guess what's happening at the surface. Think of it this way. If you wanted to know the exact temperature of a hot pan, would you hold a thermometer an inch above it, or would you touch the thermometer right to the surface? You'd touch it to the surface. Of course, using a high Y+ value with certain turbulence models is like holding the thermometer an inch away. The software has to use a simplified model to estimate the temperature at the surface. But when Y+ is around 1, you're placing your virtual thermometer right on the pan, getting a direct, accurate measurement of the physics at play. This direct resolution is the gold standard for many applications. It allows the simulation to capture the steep gradients in velocity and temperature that occur only within this tiny sublayer. These gradients are the direct cause of wall shear stress, which creates drag and heat transfer. Without placing mesh cells in this region, the simulation is effectively blind to these critical phenomena, leading to potentially significant errors in the final results and making our engineering predictions less reliable. So, this all sounds like interesting science, but how does this Y+ number actually affect the real world? The answer is, in huge ways. Let's think about designing a high-performance sports car, like a Porsche. Engineers use CFD simulations to make the car as aerodynamic as possible. They are obsessed with reducing drag, which is the force that tries to slow the car down. A huge part of this drag comes from friction between the air and the car's body. This skin friction drag is determined by the wall shear stress, which is exactly what we need a low Y+ to predict accurately. By creating a simulation with a Y+ value of 1, engineers can precisely calculate the drag on every curve and panel of the car. This allows them to make tiny adjustments to the car's shape, maybe changing the angle of a side mirror or the curve of the roof that can reduce drag by a few precious percentages. This might not sound like much, but it can lead to a higher top speed, better fuel efficiency, and improved stability on the racetrack. Without an accurate drag prediction, they would just be guessing, which is not something you want to do when designing a multi-million-dollar vehicle. The same principle applies to airplanes. For an airplane, drag is the enemy of efficiency. Every pound of drag requires more engine thrust, which burns more fuel. Accurately predicting the skin friction drag over the massive surface of the wings and fuselage is critical. Furthermore, heat transfer is incredibly important. Think about the hot gases rushing through a jet engine turbine. Engineers must predict exactly how much heat will transfer to the turbine blades to ensure they don't melt. A simulation with Y+ approximately equal to 1 is essential for this, as it accurately captures the heat transfer from the gas to the metal surfaces. Ultimately, mastering Y+ is about trust. It's about building a digital twin of a product that behaves so much like the real thing that we can trust its predictions. Whether it's designing a more fuel-efficient airplane, a faster race car, a more effective cooling system for our electronics, or even ensuring the safe operation of a nuclear reactor. The underlying physics often comes down to what happens in that tiny boundary layer. By paying close attention to Y+ and ensuring it's around 1, engineers can unlock the secrets of the flow at the wall, turning their computer simulations from a colorful picture into a powerful and reliable engineering tool.